Imagine you're walking down the street and a guy comes up to you and says, did you know that 99% of people can't do a backflip? And you're like, yeah, that sounds about right. Most of the people I know can't do a backflip. So then he says, well, what do you think the chance that I can do a backflip is? And I mean, statistically speaking, he looks like an average guy. Chances are he can't do a backflip. That's pretty obvious. So then he says, I bet you 50 quid I can. So should you take the bet? And this is a silly question, right? Like, this has nothing to do with probability. You don't need to draw out a diagram or calculate odds. It's just obvious. It's common sense. Obviously, don't take the bet because he's trying to scam you. He's probably been going up and down the streets trying to find someone that will pay him 50 quid and then he'll do a backflip. But actually, I want to try and convince you that using common sense and asking, why is this person trying to bet with me, is just as important as looking at the numbers themselves. So we're not going to be using sample spaces or probability trees. We're just going to try and solve all our problems with common sense. And the main idea is, don't just look at what you know. Ask, why do I know this? Why has someone told me this? Are they trying to trick me? Let's start off by looking at some very basic coin flips. So I'm using these Othello pieces. They're black on one side and white on the other. And we'll say, white, you win, black, you lose. I'm going to use this cup to flip them, so I go. Obviously, it's a 50% chance that it's white, 50% chance that it's black. But I can keep doing this as many times as I like. And it's always going to be 50-50 each time I do it. Okay, so how about you pay 10 quid, and if you've won, if it's white, then I'll pay you 30 quid. Those are good odds, right? You're going to triple your money. So do you want to bet? Well, too bad. It was black. But how about we play again? Maybe you'll get lucky this time. So I can flip it, and each time I flip it, it's just going to be 50%. It doesn't matter what all the other times I did it, right? Each time I do it, independently 50%. So how about now? Do you want to bet again? Do you reckon it's going to be white? And if you do, you'll get triple your money. Ooh, unlucky. It was black again. And it's clear what I'm doing, right? I'm just flipping the coin again and again until it comes up black. But just think how weird that is. It should be 50-50, right? It doesn't matter what all the previous outcomes are, but if I want to bet on it, and you know that I'm trying to make money, then you can tell that it's actually more likely to be black. So that was me trying to trick you, but it works the other way as well. So this is a similar game, but this time I want you to win. If you win, I win. So similar thing, 3 coin flips, and again, I'm going to look at them. But remember, I want you to win, so I'm going to remove these 2. Now, do you want to bet on this one? Remember, it's a 50-50 chance, and I don't get to edit that. But the fact that I've chosen this one, and the fact that I'm trying to help you win, means it's actually more likely to be white than black. Hopefully that makes sense. And indeed, in this case, this one was white, and the other 2 were black. So we can do the same again, but this time we'll make sure that exactly one of the coins is white, and we're just going to shuffle the cups. Again, I get to look at these 2, and I get to pick one of them to remove. And I'm trying to help you win, remember. So very similar thing, would you rather pick this one or this one? And it's the same thing again, right? There's a 2 in 3 chance actually that I managed to find the white coin. And even though you don't know what's in this cup, you can use my knowledge to your advantage by picking this one. And indeed, I did find the white coin. This cup is obviously not a white one, by the way. That one's obviously going to be black. Hopefully you're not surprised by that. That doesn't change anything. So this is more often known as the Monty Hall problem, which you might be familiar with. I'm not going to go into the details of how it relates to the original game show, but you can think about that if you want to. But the main thing to remember is this one is special because it's the best of 2 choices, whereas this one isn't. If I had happened to just remove this cap by random chance, then there would be nothing to differentiate between these 2 choices. So that was me giving away information based on what I'm doing, but let's look at a slightly different example. So imagine you're trying to buy a second-hand car from a salesman, and the salesman says, oh, this first wheel is in great condition, this second wheel, superb condition, this third wheel, oh, fantastic. So, do you want to buy the car? Well, what about the fourth wheel? why didn't you say about the fourth wheel? That's clearly suspicious, right? There's something dodgy going on here. But on the other hand, you know 3 of the wheels are good, so chances are the fourth one's also going to be good, right? What's gone on here? Well, again, you're being tricked. You need to think about why he didn't talk about the other wheel. So, I have another game for you, but this time the rules are a bit different. This time, you win if all 5 coins are the same colour. I'm going to flip each one so it's 50-50, and I don't get to flip them again to choose what colour they are. So, at the beginning, you don't know anything. Each one is just a 50-50. But I've looked at all of them, and I can give you some information. Like, what if I told you that this one was black? Well, that doesn't change anything, right? You're still just as likely to get all of the same colour. Yeah, that's true. Yeah. So, doesn't change anything yet. Remember, you want them all black now. So I can give you some more information. What if I told you that this one was also black? Are you feeling a bit more confident now? How about if I told you that this one was also black? Now you're thinking, wow, that's great. All I need is for these 2 to also be black and you've won. So you're feeling way more confident now, right? So would you take a bet? Well, that's too bad because they were white. But let's play again, one more time. This time I can tell you that this one, this one, this one, and this one are all white. So surely there's a 50% chance that you win, right? Do you want to bet on this one? Well, you shouldn't have. What's going on here? Well, obviously most of the time you're going to get a mix of white and black. But I'm just going to show you the ones that are more common. So counterintuitively, that means that the other ones I haven't shown you are actually more likely to be the other colour. I think it's easier to notice what's going on when there's someone trying to trick you, but it's actually a lot harder to notice when you trick yourself. So, imagine you're going on a school trip and you've taken a bunch of 6 kids. Now, you know that most kids are fine, they'll stick with the group, but like occasionally one of them will just wander off from the group and get lost in the museum. You'll have to go and find them. So at the end of the day, one of the teachers is counting up the kids and they count 1, 2, 3, 4, 5, and then they stop. And they say, well, there's only 1 kid I haven't counted, right? And the chance of that specific kid getting lost in the museum is very small because most kids stick with the group. So chances are all the kids are here. Can you notice the mistake? Obviously, the 1 kid that he didn't count is probably the 1 kid that did get lost in the museum. The teacher is only looking at the 5 that are safe and incorrectly drawing conclusions. The big idea here is confirmation bias. This idea is going to be really important, okay? Confirmation bias, you're only looking for good things, so the stuff you didn't see is actually more likely than normal to be bad. So let's go back to the game we were playing earlier. So remember, you need to have them all be the same colour in order to win. But this time, you ask me, are all 3 of them the same colour? I'm like, sorry, I can't tell you that. So instead you ask, well, are at least 2 of them the same colour? Yes, I can tell you that at least 2 of them are the same colour. So that means you know 2 of them, right? So now it's just a 50-50 chance that the other one is the same colour as the other ones, right? No, you've tricked yourself. Even though you know 2 of them are the same colour, confirmation bias actually tells you that the other one is more likely to be the other colour. This is a really weird concept. You've tricked yourself into thinking you're okay by only focusing on the 2 that match. It's confirmation bias. In fact, there will always be at least 2 of them which are the same colour. So me saying yes doesn't give you any more information. That doesn't mean that there's always a 50% chance that they're all the same colour, does it? And I should point out, because this confuses people a lot, it doesn't matter which 2 coins happen to be the same colour. It also doesn't matter which colour they are, like the order doesn't matter. What's important is that you know 2 of them are the same colour because you were looking for 2 that are the same colour. And that makes it more likely that the other one is the other colour. This is very confusing. So how about one more silly example to explain this concept a bit better? Imagine you have an audience of 100 random people, but it's kind of dark, so you can't see what gender any of them are. But, you know, you expect them to be in a 50-50 split. So you ask, is there a man here? And someone shouts, yeah. So there's at least one man. Then you ask, is there another man here? And someone shouts, yeah. And then moves across. Okay, You keep doing this until half the audience has said yes. So you know half the audience is male, but you don't know anything about the other half, right? So is the other half a 50-50 split? No. The other half isn't 50-50. Confirmation bias means the other half is more likely to be the opposite of what you're looking for. So these are more likely to be female than male. Of course, we couldn't talk about confirmation bias without talking about the most famous example. So this time we have 2 cups, and you need both of them to be white in order to win. Obviously that's pretty unlikely, right? So you ask me, is at least one of them white? I'm like, yes, at least one of them is white. So you're feeling more confident now, right? But is the chance now 50-50? Again, to be clear, it doesn't matter which one is white. So I can even show you one of the white ones. That's not going to change the probability at all. It doesn't matter the order that they're in. All that matters is we know this one is white because we were looking for the white one. That actually increases the probability that the other one is black. Confirmation bias means the other one is no longer random, which is weird. So this is often known as the boy-girl problem, where black means it's a boy and white means it's a girl or something. But imagine you're walking down the street and someone comes up to you and says, I have 2 children, at least one of them's a girl. What's the probability that the other one's a girl? Well, the correct answer is, what on earth are you talking about, right? Like, if they've said one of them's a girl, does that mean if they were both girls, he would have said they were both girls? Or are they actually both girls and he's trying to trick you? Or is it just he's chosen a random one of his children and he's just chosen their gender and said, I have at least one of that gender, in which case it's 50-50, right? And it might sound like I'm being pedantic and ignoring the maths, but that is the maths. Partial information cannot exist inside a vacuum. You always have to ask, why am I being told this information? One more example before we move on. I like this one a lot, so I kind of had to include it. So we've seen that if you ask, is at least one of them a girl? And the answer is yes, then confirmation bias means the other one is actually more likely to be a boy. But what if instead we ask, is at least one of them a girl called Tabby? And the answer is, surprisingly, yes. Well, confirmation bias means the other one is now more likely not to be a girl called Tabby. But that's obvious, right? He's not going to name both of his children Tabby. That would be ridiculous. So this actually doesn't give us that much information, and the other one is still 50-50. So far, we've seen what happens when other people try and trick you, and we've also seen what happens when you can trick yourself with confirmation bias. But there's one more thing which is very similar and technically the same, but I think it's worth talking about separately. So imagine you're holding a dinner party, and the first guest says, oh, lovely time, I loved the apple crumble. The second one's like, oh yes, I loved the apple crumble too, it was delicious. And the third one says, yes, that was amazing. And then Mona, the fourth guest, just remains completely silent. Now, this is very similar to the other examples I was talking about, but it's slightly different. No one's trying to trick you here, right? None of the other guests know what Mona was thinking, and it's not like you're only trying to look for information that confirms your suspicion. Like, you would listen to Mona, but she didn't say anything. But you can still tell that maybe Mona doesn't like the apple crumble, right? She's being polite by being silent. It's the fact that she didn't say anything that gives it away. So the lesson is, don't just look at the information you're given, think, what information am I missing, and why am I missing it? I have one final game I want to play in this video. Very similar to our other games. We're going to be flipping the coins, and if it's white, then you win. But this time, we're going to pretend the coins are frogs. Bear with me here. So let's say the white ones are female frogs, and the black ones are male frogs. The difference is that male frogs occasionally croak, like this, ribbit. Whereas the female frogs, the white coins, remain completely silent. This scenario is loosely based off an infamous Ted Ed riddle video. But the original video had many, many problems. Like, if you assume these are actually frogs, and this one croaks, then is it trying to attract a mate? In which case, is this one more probably female? Or if it's trying to attract a mate and it's already next to a frog, does that mean this one is actually more likely to be male? or even just the fact that you heard a frog croak in the first place, well, you're more likely to hear frogs croak if there are two males, because they'll be croaking more often than just one male on its own. We are going to ignore all of that. In our scenario, clearly each frog is actually just a coin toss, and we're not going to look at the time intervals in between croaks. So I'm just going to tell you which frog croaks next. And obviously, I'll pick a random male frog. So only one frog will croak each time, and occasionally we'll pause to discuss the probability, but I'm not pausing maliciously or anything. So maybe that sounds a bit complicated, but it's actually pretty simple. So here are three frogs, and each one's 50-50. We don't know anything about any of them yet. So I'm going to take us through the croaks. The first croak is this one, Ribbit. So obviously we know this one's male. Not quite sure about the other two yet. So next croak, Ribbit. Okay, so these two are both male, interesting. But we don't know anything about this one. Or do we? So the next croaks then are Ribbit, 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 Ribbit. So now you should be suspicious of the middle one, right? Why are we suspicious of it? Because it's remained completely silent this entire time. Surely if it were male, it would have croaked at least once by now. So the probability that it's female is actually very high. But it's weird that we can tell what the middle one is. Like, the frogs on either end don't know what the middle one is, and the middle one hasn't said anything. But we can still tell that it's probably female. So the important thing is, the silence is the clue. So now we have two frogs, randomly chosen, and the first ribbits are Ribbit, 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 Ribbit. So already we can be pretty sure that this one's female. Again, the silence is the clue. But the question is, when does that start? So we start off with a 50-50 chance for each of them that they're male or female. So the first ribbit is this one, Ribbit. Does that now change our odds for this one? Well, actually, yes. If this one were male, then why didn't it croak first? The fact that it's remained silent so far is already an indication that it might be female. In fact, it's gone up to a 2/3 chance that this one is female. And that might seem weird, but remember, don't just look at what we know, that this one is male. Think, why do we know this one's male? Because this one croaked first, because this one remained silent. But maybe you're still not convinced by this argument, so let's consider a different set of two frogs, but this time we won't be able to see which one's which. Ribbit. Does that change anything? The fact that we didn't know which frog croaked, does that change the probability of finding a female frog? No. It obviously doesn't matter which frog croaked, the order is meaningless. All that matters is one of the frogs croaked, so the other one is actually a bit more likely to be female. Another way to look at this is that the original probability that there's at least one female is 3 in 4, pretty high. But as soon as you hear a croak, the probability drops to 2/3. So hopefully that makes sense, that's the same number we had earlier. Either we see which frog croaked, in which case the other one increases from 1/2 to 2/3 probability, or even if we don't see which frog croaked, the overall probability drops from 3/4 to 2/3. It's the same either way you do it, you get the same number. Just to be clear, there is a difference if you hear multiple croaks. Ribbit, 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 ribbit. Now you can't tell whether that was the same frog or different frogs each time. But if you do see which frog croaked, ribbit, 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 now you can be very sure that this one is female. There's a slight difference there. So that's the end of the video. Don't get tricked, don't fall for confirmation bias, and always ask not just what information do I know, but what information am I missing and why am I missing it? If you didn't understand the logic of this video, then that's okay. You're not alone. These are famously very complicated problems. And I think a lot of people will say, just look at the maths instead. That makes it a lot more clear. But I disagree. It's really easy to spend half an hour writing out a maths proof and make one small error in how you set it up and your conclusion will just be completely wrong. It's still difficult to tell with maths. Especially with probability, it's very easy to make a small mistake and fall into a trap. But I'd still encourage you to try working through the maths yourself. The best way to learn is to try and do it from a different angle and see if you get the same results. And if you don't, then ask why. let me just say one thing about probability before we finish. So if you flip 2 coins, then there's a 50% chance they're the same as each other and a 50% chance that they're different. That might seem obvious, but you'd be shocked by the amount of people who get this wrong. It's definitely not as obvious as you think it is. Hopefully this video has demonstrated that you don't need a pen and paper and half an hour to figure out probability. If you understand the main principles, you can use it in your day-to-day life to make things better. Well done for making it to the end of the video. Thanks to my brother for filming this. Goodbye.